Welcome everybody to the next issue of the CASA Distinguished Lecture. It's mine, I think everybody else, a great pleasure to welcome Srdjan here from ETH Zurich. Srdjan and I actually go back a long, long time ago. I think we met when you were still at ETH, right? Is that possible?
ETH, yeah.
Yeah, genau. So long time ago when he was still finishing his PhD. Yeah, so Srdjan is very dear to CASA because he's also on the advisory board and has given super support in the first 1.5 years that we've been operating. This is really great. Besides being a great colleague and very nice chat partner, he's also a worldwide authority in secure positioning, which is an area which is also touching within CASA. Not quite, but it's, would be somewhere between hub A, B, and C. So it's very valuable line of research. And at least in my groups, that comes up all the time, but we never really worked on that. And so we're extremely curious to hear more about it. And Srdjan also has an ERC in that area and secure positioning, which is really great. Yeah, so lange Rede, kurzer Sinn. Thanks for coming, Srdjan, and we're looking forward to a very exciting lecture.
Yeah, thank you for raising those expectations so high. So yeah, it's a pleasure to be here and to tell you more about security of distance measurement. I will focus my talk largely on the security of ultra-wideband distance measurements, given that this has been somehow the topic is gaining more and more relevance with the introduction of all these ultra-wideband radios in mobile phones and cars and tags and so forth, right? So this is becoming an interesting topic for most of us, given the history of relay attacks, and I will essentially go over that. So I guess we all, all of us who work in this space, we have seen this kind of videos where if you notice one attacker is standing here next to a car and the other attacker is sort of weirdly walking towards what is essentially a house. So this is a Ring camera recording one attacker approaching the door and the other one standing in the background, standing close to the door of the car. What they're doing, one is exciting a key, a passive keyless entry and start system key fob, which is in the house, and relaying to the other radio held by his partner here close to the car. And the car, as you saw, unlocks, and then they can sit in the car and drive away. So that's a convenient way of stealing a car, doing something called a relay attack. And you can find this video online. So, and what it essentially shows is it shows this relay of the interaction of what is now a kind of conventional key fob, which is shown here, and the car, where a car and the key fob establish proximity by communicating on a low frequency channel here, which is this channel, this short range, sort of roughly less than 2 meter channel, and with a reply being sent from the key fob to the car on some UHF channel. The main sort of idea in this approach is that if a key fob can hear the car's challenge, and the car is constantly transmitting these challenges, then and if the key fob then replies, and all of this, of course, is a challenge response protocol with shared keys, meaning it should be sort of robust. So if the key replies, that implies that the key is close to the car. So proximity is somehow established using this notion of being able to communicate. So being able to communicate implies proximity, and in benign settings typically it does, right? This LF channel, this LF radio should not be able to communicate with the key fob roughly further than those 2 meters. So this sort of roughly makes sense. Now, it was very easy for us to launch a relay attack on this already in 2011, and first with a cable, and then with a radio setup where we would pick up these challenges by the car, relay them to the key fob, and then the key fob would reply back to the car. And these relays worked perfectly both for opening the car and also for starting the car and driving away. Yeah, but of course this is not this kind of notion of measuring the distance and also measuring the distance securely and also of relay attacks is not unique to cars alone. Recently, I was involved in this contact tracing, digital contact tracing project called DP3T that later on inspired, or better say, Google and Apple took over for the design of their contact tracing system, where we wanted to design a privacy-preserving contact tracing system where different phones would exchange what are essentially pseudonyms, and as phones get close to each other, they will record the pseudonyms that the other phones are broadcasting, and then based on this interaction, if two phones exchange these pseudonyms, that would mean that they are essentially close, and that would mean that potentially infection might have happened, right? The contact happened and therefore infection was likely. So there is a whole system behind it that would then allow you to check whether you were in close proximity to someone who is infected. Now, we knew during the design of this system that we cannot get around one issue, right, which was an issue of relay attacks. And it has been, of course, shown in practice by a team in Darmstadt, and they showed that what one could do is one could essentially relay the beacons, or I mean the pseudonyms that are being transmitted by an infected person to another location, and therefore convinced all the other phones around that new location that they are also, I mean the owners of those phones, that they might also be infected. So in some sense you could imagine running these relays across the entire city and spreading some sort of wide panic among people just because you can do a relay attack. And there is practically nothing that we can do to prevent this, since this communication, this exchange of these pseudonyms relies on beaconing mechanisms of Bluetooth, which is a short-range communication technology currently available in all the smartphones. So preventing these kind of wormholes is rather hard, and this is one place where we would really need something like secure distance measurement, because then we could establish proximity between devices securely, and then we could build the entire system to be robust against these kind of attacks. Of course, a similar scenario could be applied to cars that are approaching each other, and if their distance can be impacted by the adversary. Clearly, if the cars are approaching each other and the adversary can convince them that they are further away, they would just smash into each other without noticing. I mean, I'm here, of course, this is a little bit of a kind of sci-fi scenario where we have autonomous cars driving and making these decisions solely based on these distance or location information that is provided, that can be spoofed by the adversary, right? So, but this secure distance measurement and more generally secure positioning is something that, of course, we could use in payments. So if you want to prevent, for example, relay attacks on the contactless payments, we want to use it in access control. Being close to your device or being further away from your device would unlock it. You want that to be secured. And what you don't want is that these mechanisms work in some scenarios so that you have secure distance measurement technology that works in one context and then doesn't work in another context. So works for cars but doesn't work for your laptop, or works for contact tracing but will not work for your maybe for your contactless smart cards and so on. So what I'm arguing for is that we should build secure ranging in the same way that we are building crypto, meaning that it's context free, right? When you have an encryption scheme, it should work for all languages, for any kind of data, any kind of plain text, and it should not be it should not be context dependent. So we should get something that is analogous to semantic security, right? Where it doesn't really matter in which setting you use it, but it just works. So we need, and in the context of secure ranging, this essentially means that we need a provably secure ranging that is secure against all logical and physical layer attacks. So ideally, it doesn't really matter what kind of antennas, what kind of oscilloscopes, how fast your adversary is, what kind of sampling rate he has. He should not be able to, we should have guarantees that this adversary is not able to change the measured distance in a certain way. Now, the focus of this talk and also of most research recently has been to essentially prevent distance reductions, because in most of these scenarios it is the ability of the attacker to reduce the measured distance that does most harm. So I will focus on that in my talk. But just to give you a little bit of a lay of the land, right? So what has been happening in ranging and what has been considered in the last 10 years or so. So initially in this car scenario as well, and also in other contexts, there were technologies proposed for ranging that have been shown later on not to be secure. So notably relying on received signal strength or phase measurements. So we wrote a very nice paper to show how phase-based measurement is fundamentally insecure, and there is actually a nice YouTube video on that you can watch. There are other ideas like using chirp spread spectrum. We have shown how insecure that is due to the long symbols that become quite predictable for the adversary, and so forth. So, however, what emerged out of these almost a decade, and I would say decade and a half of investigations and attacks and people looking into this problem is that ultra-wideband seems to be a promising technology in this space and could actually solve this problem of secure ranging. And it has been, so in 2017, a new working group for the 822.15.4Z standard, which is sort of a follow-up of the 4A and 4F standards that some of you might know. This task group was formed in order to propose a new standard for secure ranging. There are other standardization efforts now being started in the last year or so, and those are around 822.11az. So this is in Wi-Fi, where next generation positioning is being considered in the context of OFDM-based ranging. Now, I have my own thoughts on that, so we can go down that rabbit hole maybe at the end of the talk. But I would say the most promising one still remains ultra-wideband in terms of power consumption, in terms of security guarantees. And one of the key reasons why is that we have this very narrow nanosecond pulses over which the adversary cannot really do easily distance manipulation attacks, right? And sorry, maybe just to go back to this slide. And of course, there are a number of consortia now being formed, like FIRA consortium for essentially more IoT kind of ranging, and also the car connectivity consortium, both of which are focusing on ultra-wideband secure ranging. And of course, what probably brought this to everyone's attention, right, is the deployment of ultra-wideband within smartphones, Samsung tags, and also Apple tags, AirTags are being deployed today, and they use ultra-wideband, not as far as I understand yet for largely, for some security critical applications, but mainly for finding objects in the environment, right? And those are largely based on what is the 822.15.4Z. it's called the HRP mode. So I'll come back to those modes. And the security of this mode and of these systems is actually not open, right? So we don't really know what these companies do, because the security is proprietary. It seems to be security by obscurity, right? So you don't really know how they protect this distance measurement against manipulation. But I will give you some ideas how this can be done at the end of the talk, given that we have been given that the documentation from the standardization task group is open. So from that we can read quite a bit about how these systems can be secured. Now there's another mode in this standard that was recently approved, and that's called the LRP mode, and it seems to be mainly deployed within key fobs. One of the main reasons is that it consumes much less power, so it's currently deployed in a number of car models, and this mode has open security specifications. So I will go over that mode as well and discuss its security as well. So just to show you how nicely this can work, this is quite an old video. I don't even remember when we recorded it, but it could be like 4 or 5 years ago even. Here you can see how well ultra-wideband actually can work, right? So this is a board on which we put one of these chips, and this shows you how far you can go with this technology and also the precision that you can get, right? So you can get up to 100 or more meters of distance. In this case, this is an LRP chip, right? So it gives you that distance, and it gives you quite a high accuracy in terms of the distance. So the distance is measured between this table or the laptop and this board that my student is holding. Okay, so a little bit of background and also a little bit of clarity in terms of what has been happening in the community. So somehow there have been two parallel tracks in this community, right? So there has been a lot of research in distance bounding protocols, right? And that, there has been a lot of work in that space. And this literature actually covers all kinds of different attacks on ranging, with trusted and untrusted provers and so on. And these are valid attacks in their own context. But essentially what the industry has been focusing on, and what the ultra-wideband, this ultra-wideband standard 4Z has been focusing on, is what's called the mafia fraud attack. So it's if you want, the simplest scenario where you have two devices, V and P, and they pre-share a secret, or they pre-share a secret nonce, right? It doesn't matter. So it's essentially comes down to the same. So let's say V and P in advance pre-shared their nonces NV and MP. So they both know NV and MP, right? So they trust each other. This is like a car and a key fob. It has been built by the same company. They have the same keying material, and there is no issue of trust there, right? So and essentially one of them is going to start the process of distance measurement and send what to the adversary seems like a random challenge. So this NV here, it will be received by P. There will be a fixed processing time, after which NP will be sent back, which is also random, and will be recorded by V. And they will measure, and V will measure the time of flight, subtract TP, and measure the distance based on that. And of course, we are talking about nanoseconds, because here, 1 nanosecond is 30 centimeters. So this is the main setting, and this is all that I'm going to talk about in this talk, because the rest would potentially be confusing in this context. And again, the standard and all the tags that have been deployed and all the keys that have been deployed essentially work in this mode. And this is what's this kind of a setting where the adversary is trying to manipulate the distance measurement between V and P, namely reduce this distance, is called the mafia fraud attack. Now, as I mentioned, many distance bounding protocols were proposed in the literature, right? And a lot of them are based on the Brown's and Chaum's rapid bit exchange, right? Where instead of sending packets between devices, bits are being transmitted between individual devices. So there is a bit flying, so there's a single bit flying from V to P, and then a single bit back, and then there is a bit from V to P, and then a bit back, and so forth. So this is called a rapid bit exchange. This is not how this is implemented, and this is not practical in these wireless ranging systems. I mean, it's not practical for many reasons. So one is, of course, the time that this will take. The second one would be the power consumption that you would need. The third one would be, that you essentially need to synchronize before acquiring any data. So these kind of ideas are not very practical. So is everyone okay with the sound? Okay, sorry about that. I see a question regarding the sound, so it seems to be fine. So essentially, the standard uses round trip time of flight over packets, not over bits. And before I get into that, let me say something about the physical layer and the symbols in ultra-wideband. So in ultra-wideband, all the operations, at least in the standard, all the operations are done over pulses. So these pulses can have two polarities, which can be encoded using different modulation schemes. It can be some frequency. They can be encoded in frequency. They can be encoded in phase. And these are essentially what's being used in different nodes. Also, these symbols can encode. So these pulses can encode. You might need several pulses to encode a single bit, or you might use a single pulse to encode a bit. Now, clearly, if you're using more pulses to encode a bit, you have more robustness to any kind of effects on the channel, to any kind of noise, and you are essentially aggregating the energy over these pulses to establish whether you're looking at the right symbol or not, right? And this is very common, right? I mean, we have symbols that are quite long in our communication systems. So in ultra-wideband, here we typically have let's say a millisecond to transmit something. So these symbols can be whatever. It can be a single pulse as well, which is essentially 2 nanoseconds long. So you could have a single pulse carrying a bit, and the pulse polarity tells you which bit that is. And so the example demodulation here would be that you sum up the power of these pulses within this bit 1, and if the energy that you aggregated passes a certain threshold, you decide that this is a bit 1, and you do the same for the opposite polarity, and then you decide that it's a 0, right? So there are, of course, more complicated modulation demodulation schemes. This is really just to illustrate the key idea behind using several pulses versus a single pulse for encoding. And this is very important because the security of the system will actually depend on which one we use. And so let's assume that we are sending a single bit of information from one device to another, right? And that we are measuring the time of arrival on over this one symbol, and this symbol carries 1 bit and is composed of 4 pulses, as you can see here. Now the adversary would like to advance the arrival. So this is a key fob here, and it's transmitting some pulses, and these pulses will then fly and will reach the car and will be somewhat attenuated and will reach the car with a certain delay. And the adversary now would like to introduce this symbol earlier than what the regular propagation of this symbol would be, right? So the adversary needs to introduce a symbol here at these 4 shaded slots. So how can he do that? I mean, if he cannot if he cannot predict this bit 1, right? So he doesn't know if bit 1 will be sent or bit 0 will be sent, so he needs to guess, right? However, the adversary can be a little bit more clever because this is a longer symbol and can do what's called an early detect late commit attack, right? And what, okay, so I have some funny simulation here. So the adversary would do the following, right? Before seeing and even knowing what the bit is going to be, the adversary is going to introduce some noise in these two slots. So this noise will be neither bit 1 nor bit 0. So instead of having bits with, pulses with two polarities, it's just going to be some garbage. But then the adversary will at some point see the first pulse of the symbol that will arrive from the key fob. So the adversary now at this point sees a positive pulse. And if he knows this pulse, he knows how the rest of the symbol looks like, because the symbol is currently known to the adversary, right? I mean, 4 positive pulses are 1, 4 negative pulses are 0. And now, given that he can predict the rest, he knows how to inject the rest. And he will inject them earlier than what the regular pulses would arrive. Now, what the car will do is it would sum up the energies of these 4 slots and would record a correct bit. So the adversary essentially played this attack, and this attack can be done in practice given all the synchronizations and all that needs to be done within these systems. So trust me, this can be done, right? In all, let's say, ranging systems, you can assume that the synchronization somehow is controlled by the adversary, given the preambles that are being sent for synchronization advanced ahead of the range. Okay, so this is a problem, right? And so essentially, to prevent distance shortening attack of this sort, we need to encode. So we need to encode the message such that the receiver can check if the time of arrival estimation was manipulated, right? And I will generalize this later on to something called message time of arrival codes. But for now, I mean, you can focus your attention to one thing. How do we make sure that time of arrival is not manipulated? If we can solve that, we can solve secure ranging. And the question now was, of course, if you have a single pulse per bit, we can make the system secure, because this kind of an attack that I showed you would not work on a single pulse. But if we want to have a single pulse, we need to use high peak power, right, to transmit this single pulse. Because if you use a pulse that has a low power, then it might not be received in a robust manner, so we have a problem. So we should use something that's robust, and that's typically longer symbols. But if we use longer symbols, we might be vulnerable to the attack that we just have seen. So 4Z was introduced in 2020, so actually approved in 2020. So 3 years went into that standardization effort to enable secure ranging and to try to provide performance and also robustness to this attack. Essentially, trying to fix this right side here, trying to see how can we do secure ranging with longer symbols. And after all this has been done, and we have been involved also in this standardization effort, so don't blame me for all the issues that I'm going to show, because it's let's say a collaborative effort where one has only so much let's say influence. So the question is, does 4Z protect time of arrival? And I will show you in which aspects it does and in which aspects it doesn't. So let me give you a bit more details about 4Z before we dive into these two modes. So 4Z has been specified in 2 different modes. So one mode is a low repetition pulse so low rate mode, right? And the other is a high rate mode. Now, what does this mean, right? Essentially, you have in ultra wideband, given the regulations, you have two thresholds. One is the mean power over a certain time, right? And that's limited. So this mean power here is limited. So over an interval of time, the power of all the pulses that you send, no matter how many you send, needs to be limited to that level. Okay. But there is also a peak power limit. So within this window, you still should not exceed some peak power. So the two modes essentially make two different choices there, right? One mode says, you know what, I'm going to send less pulses, but with a higher power. And the other one sends more pulses, but with lower power. Okay. Now, this has different implications in terms of how you would build these two different types of chips. So first, notice that in this case here, you're sending pulses, which are typically 2 nanoseconds wide, right? So you send one pulse every 256 nanoseconds. In this second scenario, you're sending one pulse every 8 nanoseconds, so much denser. It might seem like a simple thing to sort of, that doesn't really matter, but it matters actually quite a bit. So this low rate mode will use binary frequency shift keying, so meaning that the pulse polarity will be determined by the frequency on which the pulse is being transmitted. So you have two frequencies, and you will get 1 or a 0 depending on which frequency you transmit the pulse. The advantage of this approach here is that you are sending at a higher power, meaning that your pulses, individual pulses, can even be detectable, right? Can be detected by the radio at longer distances, by the receiver at longer distances. Another advantage is that given that you're encoding the information in these two frequencies, alternative would be to use on-off keying as well, but let's stick now with binary frequency shifting. The advantage is that you can have a much simpler radio design because you are essentially building an energy detector, right? You are not encoding your information in the shape of the pulse in some way, right? But in the frequency. The other high rate mode uses BPSK, so this is phase shift keying, where the phase of the pulse is important, which means that you are encoding the information in the phase of the pulse, which implies a much more fine-grained synchronization with the phase, right? And also you have to build essentially a coherent receiver, right? And another disadvantage is that given that if you send many pulses, you are limited in terms of the power that you can transmit. And therefore, you have to use more pulses in order to aggregate and to extract a bit, right? Because a single pulse might not be detectable by the receiver, depending on the non-line of sight environments and distances that you're interested in. There is another downside of this approach that is strictly security related that we will come to in a bit. So these are two modes, and since these two modes work differently and have different security specifications, we have to essentially analyze them separately. So how does LRP protect ranging? So LRP uses something called a distance commitment that I will show in the next slide. It can work in a single pulse per bit mode, which is great because it's secure and no attacks can happen essentially in this mode. But it also works in a multi-pulse per bit mode. This is an idea that we worked on over the last couple of years, where we can essentially do some interesting pulse interleaving in order to enable multi-pulse per bit mode, to enable multi-pulse per bit mode to be secure against the attacks that we have seen. And we have open security specification there. HRP, so LRP is going to measure the time of arrival over the received bits. I mean, I will cover this in the next slide. So maybe I will skip introducing HRP and dive into LRP first, and then we'll cover HRP. Okay, so how does LRP measure the distance and security, right? And I will first illustrate it in a single pulse per bit mode. So all of these radios essentially need a synchronization preamble, right? So this is this preamble here. I'm showing this preamble. It's being sent ahead of the random payload. So this preamble is fixed. It's known to the attacker. It's known to PNV, and after this preamble, these bits here are being sent, which are random and shared between PNV. Okay, so this is how ranging is going. This is the packet over which ranging is going to happen. The concept of a distance commitment was introduced in 2015 in a work that we did back then with Niels Dippenhauer, where we measure the time of arrival at the receiver is measured actually over the preamble and then verified over these random bits in the following manner, right? So if I'm a receiver, right, and I measure time of arrival of a packet over a preamble, I know that that pulses of certain polarity and therefore certain bits are supposed to arrive within certain time slots, which are these here time slots. And this is where I'm going to verify my time of arrival, right? So the preamble essentially just tells me where to look for bits in the next period of time, right? So I know that after, let's say, 100, so after 256 nanoseconds, I need to receive a bit 1. After another 256 nanoseconds, I need to receive a bit 0. After another 256, bit 1, and so on. The adversary can easily introduce an earlier preamble, right? He can start the ranging, he can introduce a preamble ahead of time, but then he would need to introduce the correct pulses also ahead of time. Since these individual bits are observable by the verifier, the adversary cannot do that because he needs to essentially guess each individual bit in order to, or pulse polarity in order to win this game. And he cannot do that. So the security of this essentially is you get as much security as the length of your payload. Okay? And this works because the power of your pulses is high enough that in a real deployment, you will see individual pulses, right? Because the low rate mode allows you to transmit at a high power, right? Now, this gets a little bit more involved here. So I'm just going to flash it for you to show you a bit of the challenges that are involved. So typically when you, so I would like you to focus on this upper right quadrant, where where what is being shown is the effects of the channel and of the multipath on the received pulse. So your transmitter is going to transmit these red, nicely shaped pulses, right? But those pulses are going to those pulses are going to fly through a direct path to the receiver, but are also some of them. So this pulse will also be reflected off some surfaces, and now all these reflections of these pulses are going to arrive at the receiver. All of them shifted by different times. Now, given that these pulses are shifted, they are going to create strange effects. One of the effects, and this is a very known effect, is that your strongest peak that you observe here is not going to be an early path. Meaning that if you detect your time of arrival based on the strongest peak here, on this highest blue peak here, you will essentially overestimate the distance. So the distance will be longer than the true distance. So what you typically need to do in these systems, you need to do a back search to find an early path. And this early path needs to be of the correct polarity, because this is essentially the direct component. It needs to be of the correct polarity, and also needs to be sufficiently above the noise floor to be, well, reliably decoded, right? And this is what LRP does, right? So you essentially measure the so this is your synchronization preamble, right? You're going to measure your time of arrival on this synchronization preamble, and then you're going to look at each of these positions. You're going to look for a correct pulse. So this is a little bit more details to understand how these systems need to be built, and this is essentially how they are built, right? This is what the chips do today that are being deployed on the market. Okay, so now if we are convinced that this single pulse per bit mode works and is secure, the question is, but how do we secure the multi-pulse per bit mode? And this is what we have been struggling, and also the community has been struggling. So the paper by Markus Kuhn and Gerhard Hanke that was that essentially introduced the early detect late commit attack, essentially argued that you can have no security if you have longer symbols, meaning that that would be impossible to secure such a system where you have multiple pulses per bit. And we gave it quite a bit of thought and came up with an idea, which and they were sort of, in some way, you know, their intuition was right. You know, if you have a long pulse, a long symbol, an attack is always possible. And even if you randomize symbols, you will have issues. But if you interleave symbols, so if you have, even if the symbol shape is known to the adversary, like in this case, so you know the shape of the symbol. Four positive pulses belong to the belong to one. I mean, indicate a one. Four negative pulses indicate a zero, right? Even if you know that, and even if you give that to the adversary, you can still build a scheme where this can be secure against attacks on ranging. And how can you do that? Well, you need to essentially break the relationship between the position of the association of the pulse with its bit. Okay, so if you have a bunch of bits like we have here, we have 2 bits here, we need to reorder them in time. So instead of sending them consecutively, we need to send them. We need to randomize the time at which we send the pulses. And the way to do it would be just to interleave them, right? So the positions of the pulses that are given by the synchronization preamble will essentially remain the same, except that different pulses different bits will be associated with different pulse positions, right? This is probably not a good example because here you can still figure out what belongs to which symbol, because it's, you know, green ones belong to bit 0 and blue ones belong to bit 1. But if you now extend this to multiple bit, if you have several bits which are 1, several bits which are 0, you interleave that, the attacker cannot figure this out. So the attacker essentially doesn't know where the symbol begins and where the symbol ends in this whole sequence. And therefore he doesn't know how to predict the bits and cheat. And this is described in a paper that we wrote a while back, and it has been implemented in one of the chips, and the performance works well. Of course, this randomization is something that is pre-shared between the sender and the receiver, and it's unknown to the adversary and needs to be changed over time and so on. So there are more details in this scheme than is shown on this slide clearly. Now, in terms of the security of these schemes, what we can certainly say is that the security of a single pulse per bit gives you the probability of the attacker's success is directly proportional to the to the number of pulses that you transmit. So you have n bits or pulses, the attacker needs to guess all of them, otherwise he will fail in his shortening. If you use multiple pulse per bit with pulse reordering, our simulation results show this kind of a curve, right? Where essentially this is the number of bits that you transmit, and this is the number of pulses per bit. So let's say you have 4 pulses per bit, and you reorder 16 pulses, you will have 10 to the power of -4. The attacker will have 10 to the power of -4 probability of success. And actually, this is the upper bound on the attacker's success. This turns out to be quite an interesting and difficult to solve problem, combinatorial problem to figure out. So we were able to only produce bounds, but such bounds that we know the worst case that can happen to us. So this is the best probability that the attacker can have. Okay, so this ends the LRP part of my talk. Now I want to focus on HRP, which might be interesting for a lot of you because Apple is a great big kind of target for research, and they seem to be using HRP in their chips, at least currently, right? We expect more development in this space, given that these standards are constantly evolving. There's actually new movement in this space to actually change these standards even further, to at least refine them. So we don't know where we'll be in a couple of years. But for now, we have HRP, right? So instead of measuring the time of arrival on individual pulses and on this, the HRP mode essentially uses autocorrelation, right, over a scrambled timestamp sequence. So this is something that you might know from GPS, right? You have essentially a spreading code, and you are correlating with a copy of that spreading code locally. And where you see an autocorrelation peak, well, that's your time of arrival, and this is essentially the same idea here. So the question is, what are the parameters? Is this secure? Now, again, security specification is not public, but what I'm going to show you it seems to be a common sense how to do this, right? How to implement security in HRP, and also this is also something that's inspired by the 4Z task group document. So these are the approaches to secure HRP that have been discussed in those documents. Again, I'm not telling you anything that has been discussed in private. This is all, you can find the documents publicly online. Okay, so first to describe how this works. So the HRP has several modes, but this seems to be the mode that is used by most. This is one of the simplest modes. There is still a public preamble named sync here, right? There is some delimiter in between that I'm going to skip, and there is what's called a scrambled timestamp sequence. Now the preamble is public, known to everyone, known to the adversary, and the scrambled timestamp sequence is derived from some pseudo-random number generator with a shared key on both sides. And in order to determine the time of arrival, the receiver is going to correlate, as I mentioned, the received signal STS with the local STS copy. And this autocorrelation peak will determine the time of arrival. So this sounds like a reasonable thing to do. However, like in LRP, of course, there's multipath, right? So multipath is all over us. You have signals that bounces off all kinds of surfaces, reflects and refracts and so forth, and you and all of these copies will be aggregated somewhere. So what we are looking for is actually not the maximum correlation peak. What we are looking for is a leading edge, which is somewhere in the back search window. And this back search window is typically around 128 nanoseconds in these implementations, that is above the noise floor. So this here is the noise that has some statistics, so some average noise. We have detected the maximum peak, right? And now we are essentially doing a back search to find the leading edge. And we need to decide, how do we find the leading edge, right? And what is the criterion to find this leading, to decide that this is a leading edge and not this here, right? So how do we do that? Well, one way to do it, and this is an approach that has been discussed, is to say, okay, this peak here needs to be at least this strong, and this strength of this peak, so it needs to be at least a certain amount above the noise floor, and also it needs to be a certain up to a certain level weaker from the maximum correlation peak. Why do we need this? Well, because this image is a little bit misleading. In an actual deployment, what you would see, you wouldn't see such a clear peak here. You would see many peaks here, right? So you would essentially see a maximum correlation peak, and then you would see a lot of peaks here that are higher than this peak here. So there might be some limits how close you want it to be to the maximum correlation peak. And now, based on these two thresholds, how stronger than the average noise does the peak need to be, and also how weaker from the maximum correlation peak does it need to be. This is what we are going to use in order to see the performance and the security of the system. But before we do that, let me tell you a little bit more about multipath. Now, on the left side, we still see LRP, right? LRP is also subject to multipath, right? But the spacing between the pulses is 256 nanoseconds. So, and the sort of the channel spread of this pulse is not going to be such, given this 256 nanoseconds. The influence of one pulse will not extend to the next pulse, because there is enough of a buffer between them, right? So you are not running a risk of an inter-symbol interference, right, or inter-pulse interference. However, in STS, what happens is that you have so many pulses close to each other and so many reflections of these pulses that the reflections of one pulse are going to impact the next pulse. So you get this kind of soup of things. And what this does is, when you do the autocorrelation, it essentially raises the noise floor. And this is because of the spacing, right? So, and this is problematic both in terms of performance, but it's also, as we will see, problematic also in terms of security, because if you have more noise, your thresholds are tighter, right? So the probability of the adversary to introduce something that is a little bit above noise, but still good enough, is higher than if you have a lower noise floor, right? So so this will, of course, impact not only the performance, but it will impact the security of these systems. So what we first did in order to understand a little bit better how HRP works is to play with the thresholds initially in a benign case. So without any attacker, if we set the pulse to average, the pulse to noise ratio, so this is this PAPR here, and the distance of the pulse to the maximum peak, sorry, the distance of the early peak to the maximum peak, we have different choices, right? So we went through a number of parameters, and what you can see is that essentially, as you change these parameters, you might have errors in different environments: residential, office, outdoor, industrial, in different channels. Essentially, you might have errors in those channels even if you have no attacker. Of course, you can see here that there are scenarios, there are configurations of these thresholds that will provide you with a reasonable performance across all of these channel conditions, right? And this is done in simulation. So, you know, this of course, these numbers might look different for different implementations, but this is to give you an idea. So we might have errors even in a benign case, which is fine. LRP has errors, HRP has errors. These systems are not perfect. They are subject to some thresholds. But the following question is, can we choose a set of thresholds where the errors are low, but the security is also high, right? And I will show this in a second. But before we show that, before we answer that question, let's see if there are any attacks on HRP. And we actually, unlike in LRP, which we studied and we couldn't find attacks, we found 2 new attacks on HRP, which will be published which will appear in WiSec in 2021. The paper should be available in a few days on our pages. So here's the first attack, and it's actually a very easy attack to make. You don't need to do much, just synchronize with the pulse sequence that the receiver is going to receive. So imagine that you have a legitimate transmission that transmits these pulses that you as an adversary cannot guess. And these pulses are arriving at the receiver, and the receiver needs to decide on a time of arrival here. Now what we do is, we call it the Cicada ++ attack because it's kind of a follow-up of the Cicada attack. What we do is we introduce pulses of random polarities, right? We don't know, we cannot predict whether these are correct polarities, but of higher power than the pulses of the legitimate transmission. So we make sure that our power is higher so that we have a stronger influence, but we introduce them with a lower pulse repetition frequency, meaning instead of transmitting every 8 nanoseconds, we transmit one pulse every, let's say 32 nanoseconds or 64 or whatever, right? So we are kind of spreading it a bit. Now, as it happens, this kind of blind injection of stronger pulses with lower pulse repetition frequency has the ability to create side peaks, earlier peaks in the autocorrelation that will be detected with some probability that we will show by the receiver as early pulse. And we couldn't believe it, right? We thought that it couldn't be that simple, but I mean, at the end, I'll come back to the point, it really is, securing this kind of autocorrelation that is being used in HRP is really a daunting task. So we did that, and what we got was actually shocking for us, right? I mean, and that was that there was no configuration of our thresholds for which we would not get, so all of the configurations of threshold yielded extremely high success rates, right? These success rates are, I have to put this in context. So we consider the success here if the attack managed to produce a shorter distance that's shorter than the true distance by at least 8 nanoseconds. So, and each nanosecond is 30 centimeters, so it kind of reduced by 2.5 meters at least, right? Now, this graph here shows you, so the blue dots here are the misdetection rates across all configurations. So these are, each point here is one of these configurations here, one of these threshold configurations. And what you can observe is that threshold configurations that have that have low misdetection rate, meaning that are good performance-wise, are terrible security-wise. So if you want to have, in a benign scenario, good performance, so meaning low misdetection, meaning that your car is going to open with 99.9% probability, and your distance is going to be measured correctly in most of the cases. I mean, you are in this range here, right? I mean, these are the low percentages of errors that are here. For all those configurations, the reduction attacks have a high probability of success. Like, I mean, at least, even if you allow like 10% of error in a benign case, you get 10% of the attack success, which is still pretty high, right? I mean, if you want to steal something. At the end, at the parking lot, if I'm doing this attack, I don't need to steal one car. I mean, I don't need to steal 100 cars. I can steal 10 out of 100 and still be happy, I guess. Maybe not me, but maybe someone who cares about that kind of business, right? So, okay, but this is not the only attack on HRP that we came up with. So another one was an adaptive injection attack. So instead of blindly injecting pulses with a lower pulse repetition frequency and higher power, what you can do is every time that you inject a pulse, you can essentially check. I mean, because at this point here, I inject a pulse, and now I can see whether the pulse that I injected correlated well or not with the legitimate sequence. And I can calculate the autocorrelation and see if this produced the peak that I wanted, and if this actually produced a peak at the distance reduction that I wanted. So with this kind of adaptive injection attack, which maybe in terms of implementation is a little bit more challenging to do, you can start injecting and see and sort of observe what kind of effects you might have created, and then use this adaptive attack to be better in controlling not only whether you created an earlier peak, but where you created an earlier peak. So this adaptive attack, of course, is much more powerful than the cicada attack, but as we have seen already, the cicada attack produces already quite high attacker success rate. I'm not going to go into the details of this, it's described in the paper. What I'm going to show is that the adaptive injection can allow you to even control where you inject the early peak. So alpha here is essentially says by how much do you want to shorten the measured distance, and E here tells you, I guess this should have been epsilon, but still, right, shows you what is the tolerance that you are willing to accept. So for example, here in the adaptive injection, we can say that 17.4 here means that in 17.4% of the cases, we managed to inject an attack that reduced the distance by 100 nanoseconds plus minus 4 nanoseconds. So that was a tolerance of our attack, right? I mean, this is, of course, just one possible attack, right? What essentially worries me about HRP security, and I think we'll hear more about this in the next years as people study this more, is, we have no stated hardness assumptions in HRP, and we were. I mean, I was there at the standardization meeting. I tried to argue for introduction of some security, guarantees or to be explicit about the security of HRP, but that effort didn't get far. So we don't have stated hardness assumptions, which means that unlike in LRP, where I can tell you, look, the attacker needs to guess these bits, these pulses, in order to win this game. This autocorrelation game with the backsearch window is is very fuzzy, right? I mean, you have to, the attacker needs to, so whoever proposes a secure HRP scheme needs to essentially argue that it set up a scheme in such a way that it can detect all possible attacks which would create an early peak, right? And I have not seen such a proof, right? And this is of course worrying, and the attacks that I just showed you essentially show how, illustrate how dangerous this can be. So, other attack strategies are possible as well. They need to be evaluated. And actually, we were not able to find a set of thresholds that simultaneously achieve security and performance with HRP, right? So for now, I cannot tell you that this means that whatever Samsung and iPhone have in their phones is vulnerable to these attacks. I would guess that if they use HRP as it is, as it was discussed in the standardization task group, I believe that then they would be vulnerable to these attacks. But we are actually working on evaluating this on the available tags, right, which they just became available. And luckily, the community is fast. You can actually find the YouTube videos already now. People are reverse engineering these tags, and the code is becoming available. So I'm sure that more clarity will be out there how these tags operate, how they implement HRP, and whether it's secure or not. So whether you should use them for any security applications or not. But now the question is, okay, maybe we can secure HRP. Well, one idea would be to, instead of using these thresholds that I described, one idea would be to use more complex statistics over the full length of the STS autocorrelation, right? So we explored this in one of our papers, using the variance and the mean of autocorrelation in order to be able to detect the attacks. However, this is actually quite costly, right? I mean, computing autocorrelation over 4,096 pulses, and in order to check for this, and then doing this kind of statistical analysis is both time consuming, right? And you need to execute the payment fast or open the door fast. You have tight time constraints, and also consumes energy, right? So whether these strategies can be implemented in such low power, we don't know, and we don't know if such strategies are feasible on such low power devices, right? So this might cost both energy and time, and this is actually critical in the operation of ultra-wideband. So actually there is an alternative. So for some strange reason, a predecessor standard of 4Z called 4A did have a mode, an HRP mode, that would allow a sort of single pulse per bit. And in that mode, one can secure HRP. However, this was removed from the 4Z standard. So, you get what you get, I guess. But now I'm going to step back, right? So, and I'm going to try to convince you that everything that I told you and all of these strategies, so the ultra-wideband with pulse reordering, single pulse per bit, potentially using variance-based detection schemes, all of these are special cases of what we call message time of arrival codes. So what are message time of arrival codes? Well, message time of arrival codes are, I mean, it's a definition, right? These are codes. These are new primitives, right? You can call them new crypto primitives, or I don't even know how I would call them, physical layer crypto primitives, that protect the integrity of message arrival time. And as we have discussed before, if you protect the integrity of the message arrival time, then you protected distance measurement. And you can see them as analogous to message authentication codes, right? Unlike message authentication codes, which protect the authenticity of the message, right, and its integrity, right? Here we are trying to protect the time of arrival of the message. And so you can reason about message time of arrival codes that so MTACs as we call them, that prevent advancements of messages or delays of messages. And they can actually be very nicely specified. So we introduce these definitions. So it's essentially a pair of algorithms, an MTAC that is, so the MTAC algorithm is run over bits. These bits could be message bits, like NV in our case, so the nonce. And this MTAC here produces an encoding, which you can see as a modulation, but here we are talking about an encoding into samples. So it's a move from bits to samples that encodes a message in such a way that at the receiver, the verifier can take these samples. In this case of this talk, you can think of them as pulses, right? But in a more generic case of other types of modulation, you can literally think about samples of an ADC, right? And so at the receiver has an algorithm, verify that takes these samples and can, based on these samples, figure out if this message was advanced in transmission or arrived on time, right? And of course, if this message here, if you have the encoding such as we have seen before, right? Then you can, like single pulse per bit or pulse reordering, you can actually verify the receiver that the message has not been advanced, but it arrived in time because all the bits that you derived from the interleaved pulses match what you expect to receive. And of course you have to do it every time fresh, right? Because every time you freshly generate this NV here. But this is all in the process of, this is why you have a key here that can guarantee that you can each time generate a new, I mean, you have some key and some randomness in order to generate such an unpredictable sequence. Of course, this gets a little bit more kind of theoretical, but I really like this work because it tries to unify all and any scheme for secure distance measurement, including, ranging in GPS, secure distance measurement in ultra wideband, or any other scheme that you want. If you can show that it's a message at time of arrival, that it protects the integrity of message time of arrival, meaning that it's a message time of arrival code, you essentially solve the problem of secure distance measurement. Before closing, and I see that I'm running a little bit late, I would like to show you just a bit of performance of HRP and LRP. So these are two chips that are currently on the market. You can see that their distances their distance errors are largely comparable. I mean, there is actually a wonderful, this slide is, I just wanted to point to a wonderful paper that measured HRP and LRP chips in all kinds of environments, indoor, outdoor, distances, power consumptions, and so on. And you can search for it here. I think it's a really wonderful piece of work, not by me, and shows you power consumption and accuracy and some other things that are not security related. In summary, yeah, I think I've said it all. As I mentioned, there's a lot to be said in this space. There's a lot more happening in this space. If you asked me 10 years ago, I wouldn't have believed that I would still be working on this topic, but it seems that it's now, as active as it ever was. There are research proposals for secure ranging in 5G. There is secure ranging being discussed, being essentially a part of the standardization in 802.11 AZ. There are some publications here. I will put the slides online so that you can read at least our publications. I mean, other related work. I will try to amend the slides. And of course, I would like to thank the European Research Council for funding this wonderful project. And I would like to acknowledge my collaborators from ETH Zurich, some of my students, colleagues, also people from 3DB Access that produce chips in this space, which have helped us with a lot of evaluations and ideas and yeah, access to the technology. So thank you.
Great work. Thanks so much. That was excellent. That was a great introduction to an extremely fascinating field. Except Torsten left, but everybody else stayed in. So people are really interested in your research. Thank you so much. Yeah. If people have questions, please feel free to use the Q&A button or F&A button in German Zoom, or the chat room itself. And I'm going to read them. Yeah. Maybe I start, Srdjan. A very simple practical question, because we also do some work on physical layer security. What kind of experimental setup did you use to do this? I mean, this is extremely low level ultra wideband receiver manipulation, right? That you're doing.
You mean in the attacks that I showed, or?
Yeah.
No, the attacks. So some of our previous attacks were done in the lab, but these attacks are just simulations.
The simulation. Okay.
So these are simulations but okay, they are not. So these are simulations that are informed. So if you look at these parameters that we played with here, they are informed by actual requirements in the automotive and phone and smartphone markets. So we know what are what is the link budget that you need and so forth. So these numbers, we didn't come up with these numbers randomly. We used numbers that are actually relevant for ultra wideband use cases. And what we did is we simulated. These are IEEE models of various channels that are available, right? So these simulations, I mean, they're not very sophisticated, but I would say they're fairly. I mean, I would bet that they're fairly close to what we happen in reality.
Yeah. Thank you. So there's one question by Timo. Are you reading that? Or maybe I read it aloud. Thanks for the great research talk. I was just wondering at around slide 24, where there can be early path reflections. I thought if there's a reflection, it will be slower than the original sender, since the path from sender back.
They are slower, right? I mean, what you have is that if you have several pulses, right, that have. Okay, I don't know which slide he's referring to, but maybe this is a general thing. So depending on the shape of your pulse, right, you will have the aggregations of different pulses. So let's say that you have a tail of several pulses over a location, right? Then these tails will result in a stronger, in a stronger component. In a peak somewhere else aside from the direct path. So you can have a situation where, but maybe I misunderstood your question, right? So
yeah, Timo just said it's slide 30 maybe.
Okay, it would be good if I had
numbers.
Oh, so what? Well, okay, maybe then so this is slide 30. And I was just wondering, approximately slide 24, slide 30. I thought if there is a reflection, it is a bit slower than the original, since the path from sender back to the car is longer and thus slower. Okay, I didn't know. Are you referring to the channel affecting when the pulses from the attacker would arrive to the victim, as opposed to from the legitimate? Why don't you unmute yourself and say something? Because okay, he says yes. Okay, so So of course, you know, in the case of a car, it's actually quite bad, right? Because the attacker can typically come close to the car, right? So he can essentially have a much better channel than your key fob has, right? So this is, again, going back to that point of, are we building these systems for one use case or for some other use cases, right? So you could argue that maybe there are use cases where, or scenarios where it's going to be hard for the attacker to get close to the sender and the receiver and somehow inject, you know, things in the right time, and his injections will be distorted by the channel. I think that's true, but it's not. It doesn't work for all scenarios. So for a car, you can approach the, you know, the antenna of the car and try to manipulate things and inject them in the way that you like, right? So your channel can be great, whatever you want it to be. You could also simulate any kind of a channel to the car. So I didn't want to get, so that's why our simulations, I also have some simulations without the channel, just to show statistically how this attack works. Even if there would be, even if the two parties and the attacker would have perfect channels would have perfect channels. So no multipath, nothing, right? So the point is that the channel should not be our protection. I mean, sorry, Christoph, I know that you guys have some work where the channel is the protection, right? And this is fine. In some cases, this might work, but I'm trying to say, look, we should have solutions where we have hardest assumptions that actually we can justify, right? And so and clearly state. And if they are based on the randomness of some cryptographic material that we can generate, that's actually preferable to assuming a randomness in the environment. Although randomness in the environment could be a good kind of, yeah, hardness assumption if it's valid for certain environments.
Yeah.
But sorry, I want to allow also other questions. So
there's one more question by Uno Ogus. He said, "Great talk, thank you very much." And then his question is towards the beginning of the Q&A. Are new distance reduction attacks successful for consecutive rangings? In other words, for DSTWR ranging, can an attacker consistently reduce the distance same level for consecutive rangings?
Yeah, so this is what this analysis tried to show, right? So this is the probability of doing it once, right, for different distances that you want to reduce. So let's say if you want to reduce, this is for a particular, you know, receiver thresholds, right? So you have here some numbers. It depends on your tolerance of a distance. So let's say that you on the accuracy that you want in consecutive distance measurements. So let's say that your accuracy in consecutive distance measurements is let's say 12 nanoseconds. Well, then you are already getting into trouble, right? Because you might have, you know, 24% chance of the attacker of reducing to that distance in each attempt, right? Now you can say, well, maybe in my system, you know, I have I'm going to repeat this, but also the problem in repeating the measurement. I agree with you. You can repeat the measurement many times, but then maybe you have to wait for a few seconds for your car to open, and this is not really desirable, right? So there is a question of how much energy you are using when you're doing that, right? Which, in my mind, this would be wasteful, right? And second is that the overall time for the user experience might be bad. So there are certain, I guess, parameters there that one needs to also consider. But in principle, yes, why not repeat the measurements, right?
Yeah. There's just one more question coming in on the chat.
Denial of service is preferable to distance reduction. Well, if you're, I see that you're from Valeo. I don't know who your customers are, but I don't think that. I mean, as from what I know in this industry, I don't think that someone who buys a Bentley or a Mercedes wants his car not to open when he approaches it with a key fob in their pocket. I guess not. But hey, maybe we can teach the users to live with that. Who knows? Again, I mean, I don't know why you would, why one would expose oneself to this. I mean, we have, I think, better guarantees with, for example, LRP or other modes in 4A, for example.
Okay, thank you very much. Are there any more questions from the audience? A lot of specialists in this presentation.
Please keep on typing questions, but I love this mode, right? Because people cannot reply. I can just say stuff. They need to type. I mean, it's very asymmetric and gives me all the power to answer the questions at length.
I'm sure Timo hates it.
Yeah, I'm sure this would frustrate me as well. That's what I'm saying, right? So, but I understand.
Yeah. So again, I think it's really great stuff. Maybe one final question. And this Apple, also this physical layer protocol, the modulation scheme and so forth, is this all proprietary or?
Okay, so for 4Z, everything is open.
Yeah.
For HRP, so for LRP 4Z, everything is open, except the implementation, right? I mean, but the security of it and all of this is open. In HRP, the message format is defined. The problem is that in HRP, you don't know how they generate the STS sequence and how they do the detection of how do they decide after they receive the STS sequence whether this is secure or not.
But the modulation itself is part of the standard, yeah.
But the message format for HRP is a part of the standard.
Okay.
So Mohammed asked a question that 4Z presents so HRP presents STS as the main protection against distance manipulation attacks, but for my presentation, it seems that STS is basically useless at preventing. Yes, that's correct. I mean, our attacks show that STS does not protect in the way that it has been, imagined in this working group, does not prevent replay attacks. Relay attacks or distance shortening attacks like early detect, late commit. It's going to probably prevent replay attacks. Yes, any distance measurement technology would prevent simple replay attacks where you amplify the message and transmit it, but it would not prevent more sophisticated attacks. What actually makes me a bit angry about STS and the whole way that this HRP has been handled is that in the end, these companies and whoever is using HRP should say, this is how we make it secure, right? I mean, this is we use autocorrelation in this way. Here is our security argument. Here are our thresholds, and tell us if it is or if it isn't secure. We have nothing like that, and this is, I mean, why would I? I mean, if I was the one choosing this, I wouldn't buy this kind of a product because, well, it's kind of black box, whatever, right? And it's a little bit frustrating, but I mean, I think this is bad for those companies because as I've shown, people are already reverse engineering these AirTags, and I'm sure that in a very short time, we will know more about how HRP is exactly used in these different products. And they might surprise us with something good. They might surprise us with something less good. Let's see.